acceleration, letter H. Oh, yes. Thank you. So let me, and also let me change to writing. Okay. So H, acceleration. So acceleration A of t is no other than either the first derivative of the velocity or the second derivative of the position with respect t in this case. Alright, so we got the function s of t, or let's get started from the velocity function in fact. So, okay, can you please turn your phones off? I would appreciate that. So the velocity function, which is given by, we got it here, almost at the beginning, 36t squared, 3t squared minus 24t plus 36. So that's the velocity function, 3t squared minus 24t plus 36. And find the acceleration function, which is the derivative of this velocity function. That would be, okay, that's a 6t, and the derivative of negative 24t, that's just minus 24, and the derivative of 36 is just 0. So that's the acceleration function. And they're also asking us what's the acceleration after 5 seconds, or 5 seconds, a of 5. And ultimately all we have to do is substitute 5 whenever we see the letter t and simplify the expression. So that is 6 times 5 minus 24, which is, okay, 30 minus 24, is that a 6? And the units for acceleration are meters per second squared. Right, so let's be consistent with units and all that. Okay, so number one, the last part H, that's part I. When is the particle speeding up? And when is the particle slowing down? All right. Well, so there's a couple of pieces of information that we need to have together for number one, speeding up, and another couple pieces of information or conditions for slowing down. So a particle speeds up when both the velocity is positive and the acceleration is also positive. So the fact that you step on the gas, you're going to speed up. Therefore, you're going to accelerate positively, and consequently, you will get a larger velocity. As opposed to slow down, you step on the brake. That's when both the velocity is negative and the acceleration is also negative. Alright, we already solved that inequality for velocity when we covered this last time. So in this case we need to solve the inequality for the acceleration. So for acceleration, number one, let's set up an inequality a of t greater than 0 to find out the interval in which the acceleration is positive. Well, so we're going to set the inequality as the second derivative 6t minus 24 greater than 0. Solve inequality. This is a baby linear inequality. That's a 6t greater than 24 and t greater than 4. So putting this together, what we got. So I'm going to write down I'm going to draw the result of the inequality for the acceleration A, which in this case, well, the critical value of the inequality is 4, and in this case is positive for values of g greater than 4. Also, I would like to go back to the inequality. Well, actually we restricted the domain for the first 9 seconds. So we also had an inequality for the first 9 seconds for the velocity, and this is what we got for the velocity. We did it from 2. We got the critical numbers 2 and 6, for which in this case we got positive, negative, and positive. This is what we got from last time. Let me go back to show you that picture. Didn't we get that? So all I'm doing is rewriting it again. So, alright, so in this case we want to know when is this particle speeding up and when it is slowing down. So 0 to 9. So in this case we are going to put together the two inequalities together. In this case, let me extend this 6 to over here. In this case, both overlaps here. This is the region in which both the velocity and the acceleration are positive, because for this region right here on the second graph, here is positive, here is negative. So in this case we can conclude that there is another place where it's also, there is an overlap actually from 2 to 4. How come from 2 to 4? Well, that's right, because when we have this negative times that negative, when we overlap these two, we will also have this, so it's also negative here, and times negative, this is where speeding up on the intervals from 2 to 4 and 6 to 9, and slowing down everywhere else. So we don't need to shade these regions, because that's going to be from 0 to 2 and from 4 to 6. Alright, that's where these two overlap. Alright, so this completes the first part of the section, which is applications to motion, to applications in physics. Again, in summary, so the key points here is that the first derivative of a given function, a given position function, that's going to give us the velocity, and the second derivative is going to give us the acceleration of the particle going along that same line. So let's do another application, which in this case is the law of natural growth. So it's a model that you have used before, whether in intermediate algebra or what else, pre-calculus, college algebra, depending on the course you have taken. And so the idea is that this dy dx equals ky. It's telling us that the population size, if we apply this to population growth in a community, changes with respect time. If we redefine this as dp dt equals kt, So the rate of change of the population with respect to time, well, changes with respect to time. You know, we have a different population. We had a different population in San Diego a month ago, perhaps a year ago, and we were going to have a different one in the next couple of years, in the next 5 years, and so on and so forth. So that's how population changes. And of course, this model is the simplest population model because it's not considering many other factors like limited resources and, well, the size of the community, the physical size, for example. So there's a lot of factors that are not considered. But the thing is that we have seen this model right here. Back in pre-calculus, you work with this exponential model, y equals y initial e to the kt. And in this case, well, that exponent k, or that exponent, if k it's a positive number, then we're gonna have growth. But otherwise, if k is a negative number, that's gonna be decay. You might remember this model, this exponential model. You use it to solve problems, population of a community, or you were given, the half-life of a radioactive element is boom, that's time. In that case, you use it to model exponential decay, right? For radioactive decay. So let's look at one example to get this model at work. All right. So what do we have? Suppose a culture of bacteria is modeled by exponential growth, and after 3 hours there are 10,000 of bacteria, and after 5 hours there are 40,000 bacteria. How many were there initially? So yes, even though this looks like x and y and x and y, well, in fact it is x, y, and x, y. This is not going to be the information to find the slope between 2 points, because this is not going to be a linear function. Population doesn't grow at a linear rate, it grows at an exponential rate. So we have to use this exponential growth. So in this case, let's call this x and y. So using this model, this exponential model, y equals y initial e to the kt. So for the first pair of information, after 3 hours there are 10,000 bacteria. That means 10,000 equals y initial, which we don't know, that's what we need to figure out, e to the k times 3, or we can simply call it 3k. Alright, where that 3 is the x value, the time, and the y value is the amount of bacteria. And also they're telling us that there were 40,000 bacteria after 5 hours.
What does the decay symbolize?
It's a decay constant, which determines whether it's growth or decay. It's like the slope in the linear equation, but in this case for the exponential function, it's just a constant of proportionality. We will also find out what that is. In fact, that's the first thing we are going to find. In fact, well, this creates a system of linear equations. Alright, so in this case, well, it's not a system of linear equations, it's a system of exponential equations. There's a couple of ways to go about this. I mean, I could solve for the exponential on one side and then substitute it on the other side, on the other equation. But I think so a good technique to solve this system of equations that usually are kind of weird to solve. So in this case is to divide the equation. So let's label the equations. Number 1. So divide 2, by 1. You can do the division of 1 by 2, but I'll show you in a second why is dividing by 1 better than dividing 1 by 2. So that's a 40,000 equal to y initial e to the 5k over 10,000 y initial e to the 3k. So it's better to divide it in this order, because notice how we're gonna get integers, nice integers, as opposed to getting rational numbers instead. And also when we subtract the exponents e to the 5k minus e to the 3k, we're gonna get positive exponents. Otherwise we would have gotten negative exponents. So we can cancel the y initial. And so 40,000 over 10,000, that's a 4, equals to e to the 5k minus 3k, which is e to the 2k. All right, and we can keep solving this equation for k, which is the constant of proportionality, or the rate constant. That's well, let's do the inverse of having exponential. What's the inverse of having an exponential? Let's take ln to both sides. Ln by both sides, cancels ln with e, and 2k equals ln of 4, and k equals to 1/2 ln of k, which is approximately, let me do it on the calculator first. So, not ln of k, it's ln of 4. And 1/2 ln of 4. So it's 0.6931. So usually these calculations, we carry them to 4 decimal places. When you're solving a problem like this, do not round until the very end. So I'm gonna round it like this just to write down the exponential model. So in this case, I'm gonna go back to the original model. So y equals y initial e to the kt becomes y equals y initial e to the 0.6931. That's actually it's t, right? Because that's k. That number is k. So well, we're gonna use this model now to find how many bacteria were initially. Well, so that's kind of a cryptic sentence, right? So we need to figure out what's the time initially. So what's the time initially? 0. So that means we're going to plug in 0. So initially, so okay, that's the question, right? So y equals y initial e to the 0.6931 times 0, which is y equals y initial e to the 0, and that's y equals to just y initial, right? And in this case, well, we're not looking for the numerical value unless they're giving us any other information. No, so after 0 hours, we don't know after 0 hours, right? So, all right. Huh?
One of the 2 data points.
Yes, actually, that's right. We can use one of the data points. Okay, let me go back to that. I'm going to leave it like this to find the value of the initial population, right? So we can, now that we know this, let's plug in y, which, well, in this case is, how about 10,000? 10,000 equals y initial e to the 0.6931. How many hours is that after 3 hours?
Yes.
Whoops. 3 3 hours. I'm going to multiply this number times 3, the number I obtained before, and then exponentiate. So that's y initial e to the roughly 2.0794, and y initial, well actually yeah, that's going to give us the y initial, that's 10,000 over e to the 2.07, it's not a 6, it's a 0.0794, and 10,000 divided by, that should be approximately 4808. Actually, well, I get this on the graphing calculator, 0.998, but we can approximate this to the next integer. All right, so that's the initial population that we have, and it makes sense, you know, because well, after 3 hours we had 10,000, after 5 hours we got 40,000, so it got increasing, so it would make sense to have a smaller number than that value after 3 hours. If we get a number larger, well, that's kind of weird. All right, double check your calculations in that case.
In the calculator, did you put e, or did you just divide by 2.07?
No, I do the division. So let me show you how I do it in the graphing calculator. So the way I would do it, that's number one, I did 1/2 ln of 4, and that's that number times what was that, 3,
Yes.
and then
10,000.
10,000
Divided by.
divided by e. Oh, wait a minute, e to that value, so e second. I forgot to exponentiate.
Yeah, I thought it was some value that's small.
Yeah, to this number. Yeah, so it should be 1250.
Yeah.
1250, yes.
0.05.
I forgot to exponentiate. So this is, and it's actually a nice number, 1250. Well, it still makes sense that we got a smaller number, right? Otherwise, we get a larger number. That's kind of weird. All right, so I think this concludes this section. For the next section, we're gonna do more applications of derivatives, and I believe this related rates section will be the last topic that will be included on the second midterm. I have to verify that. All right. Yes.
I believe on the midterm thing it says 3.10 is also.
3.10? Oh, okay, so 3.10, which is, I believe, differentials, right? Or I'm not sure what it is.
Yes, right.
So, okay. Related rates, another application of derivatives, and well, so we already did a basic application in which we just relate the rate of change of the dependent variable with respect the independent variable. For example, when we want to change, we want to see like what the marginal profit is. Well, we find the derivative and evaluate that derivative for a different number of items sold on the profit function, rather the derivative, and that's going to tell us whether we're making money or we are losing money. And same for the derivative for the previous couple of applications. For velocity, all we did is take the derivative of the function with respect to t to get the velocity and the acceleration. However, in this case, all right, we're going to look into another situation in which we are going to have. I wish I had a balloon here so I can show you a simulation or something. But well, think of a balloon being either inflated or deflated. Well. And let's assume that this balloon is perfectly spherical, just for the consistent with the formula that we're going to use when we solve this with the problem that we're going to do. Well, so when we are inflating a balloon and you're blowing inside of the balloon, well, what's going on? The radius of that sphere increases, and as a consequence, the volume of that balloon gets bigger, or even the surface area generated by that balloon gets bigger. But that's when we are inflating the balloon. If we pop the balloon, we just do like a little pulse and we let the air escape. What's going to happen? It's going to happen. The reverse is going to happen, and in that case, it's the radius of that balloon getting smaller, and consequently both the volume and the surface area of the balloon are going to get smaller. However, we get these changes with respect to time. In fact, these are the two variables, the dependent variable, which is the volume, and the independent variable, which is the radius. They are both changing with respect to time. That we didn't have in the previous situation, in which all we did is differentiate the function, plug in for different values of t, boom, that's the answer. Well, in this case, we need to review a little bit of implicit differentiation, because, well, you'll see how this will be, how will come into play when we do these related rates. Well, find the derivative of y that depends on t cubed. Well, the derivative of y to the third power, isn't it 3y of t squared? And by mini chain rule, what happens with this dy? What do we do with this dy? Don't we differentiate it? However, this y no longer depends on x, as what we did back in implicit differentiation. This y depends on t. And well, this will be 3y squared of t dy dx. So in this case, this function is no longer depending on x, it's actually depending on t. Let's do an example in which we're going to do the whole thing. So this time we have a function, all variables x and y, and even if we had a third variable, z or w, u and v, well, many variables, all these variables vary with time. So that's, you can think of this third party variable coming into play here. So essentially, okay, so we have this equation, x squared plus y squared equals 25. Number one, what would be the graph of that x squared plus 25 equals to 25? What does that describe? It's a circle, more specifically.
A 5
Radius of 5, and what else? And its center at the origin. So let's draw the picture. So I think the picture for sure is going to help us a lot. Okay, so we're going to have this circle, and we're going to have all these points, x and y, but these points are now going to depend on time. X of t, y of t. So we can think of this particle moving along the circle at different times, and in that situation both x and y are changing with respect to time. So in this case, I'm going to redefine this x squared plus y squared as x of t squared plus y of t squared. I'm gonna do this only for this example, just so you can see the bigger picture of what related rates are about. Alright, so we're going to differentiate the quantity x squared. The derivative of x squared, isn't it just 2x? 2x of t. But in this case, we're going to do a mini chain rule, because this x is changing with respect to time. Alright? Plus the derivative of y of t squared, that's 2y of t. But at the same time, this y, it's still depending on time, so it's changing with respect to time, dy dt. And that derivative of 25 is just 0. So I'm going to erase these times from x and y. And this is going to give us 2x dx dt plus 2y dy dt. So you might see similarities from this and the implicit differentiation. But what's the difference? The main difference when we differentiated this implicitly, we just said the derivative of 2x is just 2x because we were differentiating with respect x, plus 2y dy dx. In this case, we were looking at a function y changing with respect x. In this case, in related rates, we have both variables x and y changing with respect a new background variable, if you will. There's something in the background changing besides those x and y, and this thing in the background is t, particular time. So that's the difference. Well, so they're asking us to find, so this is actually the equation that relates the rates. This equation, that's why we call it related rates, because we're gonna do some implicit differentiation, but this time with respect a new variable pulling the strings in the background, which in this case is t. And well, this equation that we obtained initially, it's the equation that relates those rates. The rate of change of x with respect that background variable, and the rate of change with respect that new of y with respect that background variable. Well, what do we have? We have x, which is given here. We have y, which is given here. We have dx dt, and the question is dy dt. That's actually the question. All right. So plug in everything we know. So 2 times x, which is 4, and times dx dt, which is 2. All right. So plus 2 times y, which is 8, dy dt. That we don't know. That's the question here. So just so we can relate this, well, 2 is 2, x equals to 4, dx dt is 2, 2 is 2, y equals to 8, and dy dt is dy dt. That's our question again. All right. So that's going to be 2 times 4, which is 8, and 8 times 2, that's a 16, plus 16 dy dt equals to 0. And what are we going to get from here? Well, let's just solve this baby equation for dy dt. So I'm going to go here. So that's 16 dy dt minus 16, or actually equals to negative 16, and dy dt equals to negative 16 over 16, which equals to negative 1. Okay, what if we go to that point, to the point x equals to 4, y equals to 8? All right, it's going to go basically here. That means that's the slope, essentially negative 1 at that point. Right? That's the rate of change, dy dt. So that's how fast is y changing with respect time. It's changing at a rate of negative 1 over 1, if you will. All right, let's see if we'll get the chance to look at least at one word of problem. Not yet, we're gonna have some time. All right, let's apply this to word problems. Let's look at the very classical problem in which we have a spherical snowball. But what happens to that snowball? Well, of course, after a while it starts melting. All right, and well, in this case we have to make assumptions. So we will have to assume that this snowball rate melts uniformly. That is, it keeps its spherical shape every single time. All right, and they're telling us that at the instant at which its radius is 20 centimeters, its radius, its decreasing at a rate of 3 centimeters per minute. So that's the piece of information that they are giving us. The question is, at what rate is the volume of the snowball changing at that same instant? Well, diagram. Well, let's draw snowball. Assume it's spherical. Well, what's going on in this case? So in this case, it's melting. The fact that it's melting, it means that the size of the snowball is reducing. In other words, this ball is shrinking, isn't it? It's getting smaller, and that's because, and consequently, that makes the radius to make smaller. Or in other words, if the radius of the sphere gets smaller, when the volume also gets smaller. All right. So here is where we also need to know our formulas from basic geometry. So since in this case we're talking about the volume of the sphere, we need to know the formula for the volume of the sphere. All right, and that formula is volume, and that's a V equals 4/3 pi r cubed. So that's the formula for the volume. Well, that's what I call the plain vanilla formula. Because this time those two variables, both volume and radius, are really handled by time. This volume now depends on t, and so this radius depends on t. Alright, so that's all we're doing. We're introducing that new variable, that third-party variable, or that background variable governing this new situation. Alright, let's write down the rates that we're given, or all the information that we are given. So, rates. So in this case, well, number one, radius r equals to 20. So they're asking us a particular question. They're asking us how fast is the volume changing at the moment when the snowball is already 20 centimeters. Well, in this case, they're telling us how fast the radius is decreasing. Notice the wording here, because, well, dr dt, which is the rate of change of the radius with respect to time, so that's centimeters. That's what was that? Negative 3 centimeters per minute. In this case, the wording will make a difference on the signs that we're going to use for some of the pieces of information. In some cases, they're not going to tell you, oh, negative, positive. No, in this case, we need to use the context of the problem, because the radius is decreasing. That is, that rate of change has to be negative because it's reducing. So that's the radius and the change in the volume with respect t. That's the unknown one. That's the one that we have to figure out. Well, so let's take the derivative. Well, be careful. If we were doing just regular rates of change, we would have done dv dr equals to 3 times 4/3. That's 4 pi r squared. That's only to see how fast is the volume changing. No, not dt. It's with respect its radius. That's just the regular rate of change between the dependent and the independent formula. But this is not what we're looking for. This is not. Let me cross it out. In fact, we are using this equation here, the one in which both variables, the volume and the radius, are changing with respect to time. So v of t equals 4 pi over 3 r of t quantity cubed. Okay, so all right, so let's differentiate. To find the derivative, dv, but notice how this volume depends on time, that's dv dt. And that's going to be 3 times 4/3, that's 4 pi r of t. 3 minus 1 is 2, but furthermore this radius changes with respect to time, so that's why we multiply by dr dt. Okay, and well, so let's see what do we have. Let's see what they're asking us for again. So we know the radius at the time, at whatever time. We also know the rate of change of the radius with respect to time, and in this case they're asking us to find put a cross instead. We don't know the rate of change of the volume with respect to time, so it's time to have all to substitute and solve the problem. All right, so well, in this case dv dt equals to 4 pi, that's 20 centimeters quantity squared times negative 3 centimeters per minute. Well, in this case let's just multiply. Okay, 20 square, isn't that a 400? And 400 times 4, that's 1600, and 1600 times negative 3, that's a negative 4800 pi. And let's be consistent with units. Notice how these centimeters get squared to give us centimeters squared, times these centimeters, that's going to be centimeters cubed, and per minute, just per minute. And the units, they should be consistent all over, because in this case these are units of volume per minute, per time rather, units of volume per unit of time. So this was our first example in solving related rates. In the future, guys, so just as a comment, you don't have to write this parenthesis t for every single equation. I did it this time just so I can show you how everything is changing with respect to time in the background. But in the future, you will not see me doing this. All right?